So derivatives of trig functions.
I thought it was today.
Remember that derivatives can be defined as the slope of the tangent line. So this can be used to determine the derivative of trig functions. If we use the graph of sine theta to determine the derivative of y equals sine theta. Right? So remember again that the derivative can be used to find the slope of the tangent line. So what we do know is that at max and min points, the tangent lines will be horizontal, which means that the slope there is 0, right? So the derivative f prime at pi on 2 is 0, and f prime at 3 pi on 2 is also 0. So if we look on the unit circle and see specifically what's happening at those 2 points, at pi on 2 the coordinates are 0, 1, and at 3 pi on 2 the coordinates are 0, -1. And what we see that those 2 points have in common is both of those points are where the cosine equals 0. So this would lead us to believe that perhaps the derivative of sine equals cosine. That leads us to believe that perhaps if f at x equals sine theta, then perhaps f prime x is equal to the cosine of theta. And we'll put a question mark after that. And so what we have here on the next page is we have the proof to see that that is actually true. So we'll go through this. Remember our formula for a derivative using first principles was a limit formula. We had 2 different ones that we used. One as the variable approached the non-permissive value. The other was always as h approaches 0, where the denominator was h. Remember the other first principle one when we used where the variable approached 0? Then the denominator was always x minus a, where a was the non-permissive value. So we looked at different strategies to solve those limits using those 2 formulas. So if we use that first formula, f at x plus h minus f at x all over h, the limit as h approaches 0 of that. So you're going to let, instead of f at x, you're going to have sine x, because y equals, or f at x equals sine x is what we're starting with. So that gives us this next statement. Okay? Now, because you have sine of x plus h, you can use the sum identity for sine. Sine A cos B plus cos A sine B. So that's what this next line shows us. We're using the sum identity for sine. Okay? Now, if you put the first and the last term together, you can take out a common factor of sine x. So this cos x sine h moves to the end. We put the first and the last term together and take out a common factor of sine x. That leaves with cos h minus 1 plus that last term. And then we use our property of limits to break these up. We can take this first expression over h plus the second expression over h. And we do our individual limits. Also, because we're finding the limit as h approaches 0, anything involving x is a constant, or not a constant, but it's not affected by h. So that's why this sine x here, which came from the sine x factor up here, that's why it can come in front as a coefficient. And same thing with this cos x here. because you're evaluating the limit as h approaches 0, that has no effect on the cosine of x, so it can come in front as a coefficient. Right? And then look at the end here, you've got the limit as h approaches 0, sine h over h. Well, we saw last week that that equals 1. Right? So that's that part there. The other thing that we did here is for this expression, we multiplied top and bottom by the conjugate of the numerator. The numerator is cos h minus 1. The conjugate of that is cos h plus 1. So multiply top and bottom by that. And that gives us this statement right there. When we multiply out those conjugates, we get cos squared h minus 1. And again, this last term, cos x times 1 is just cos x. From the Pythagorean identity, again, we know that sine squared theta plus cos squared theta equals 1. So sine squared theta equals 1 minus cos squared theta. And if you multiply both sides by negative 1, you'll get negative sine squared theta equals positive cos squared theta minus 1. So that's why cos squared h minus 1 can be written as negative sine squared h from that Pythagorean identity. Then we break up, because this numerator is negative sine h times sine h. So we can break that up, first bringing the negative sign in front, which is here. And then you got the sine x, right? And then this will be sine h, the first sine h over h, and then the second sine h over the cos h plus 1. And once again, the limit as h approaches 0 of sine h over h is 1. So that's where this 1 comes from here. So you've got negative sine x times, now at this point we can evaluate the limit, because 0 is no longer a non-permissive value. We've gotten rid of all of our factors of h. So now we'll evaluate this by letting h equals 0. So you've got the negative sine x times the 1 times, when sine, you can find the value of this limit by letting h equals 0. So that's what this shows, sine of 0 over cos of 0 plus 1. And then you got the plus cos x, which is right there. And the sine of 0, well, at 0, the coordinates there are 1, 0. So you're going to get 0 over 1 plus 1, which doesn't really matter, because you're going to get 0 times 1 is still 0, times negative sine x is still 0. All you're left is this plus cos x. 0 plus cos x equals cos x. So that's the proof, to show that the derivative of sine x actually is cosine x. On the next page, the derivative of cosine is negative sine. And again, this can be proven. So this is proven using one of our related angle identities. If you look on your formula sheet, you'll see that the sine of pi on 2 minus x is equal to the cosine of x. So the cosine of x equals the sine of pi on 2 minus x. So if we start with that relationship, and that's what we take the derivative of. Now to differentiate this, you have to use a chain rule, because inside the bracket is not just x. So we've seen just a few minutes ago that the derivative of sine is cosine, so that's where this part comes from. Derivative of sine is cosine, and then remember you're also multiplying by the derivative of what's inside the brackets. Now pi on 2 is a constant, and the derivative of a constant is 0. The derivative of negative x is negative 1, so that's where you'll get this negative 1 from. And if you look on the correlated angle identities on the formula sheet, the cosine of pi on 2 minus x is equal to the sine of x. So that's where that sine x comes from, times the negative 1, which is the derivative of pi on 2 minus x. Sine x times negative 1 is negative sine x. Okay? So we've seen that the derivative of sine is cos, the derivative of cos is negative sine. These are on the formula sheet. If you look on the formula sheet, the derivatives are all there. But let's see how we can apply this to finding the derivatives of expressions involving trig functions. In most cases, you're going to use the chain rule to do this. So if you want to take the derivative of y equals 3 sine x, then dy by dx equals The derivative of sine is cos, so it'll be the cosine of 3x, times the derivative of what's inside the bracket. So times the derivative of 3x. And the derivative of 3x is just 3, so it'll be 3 cos 3x. There's the value of that derivative. Again, you're going to be using the chain rule for these. Number 2, if y equals the sine of x plus 2 is what you want to find the derivative of, then dy by dx will equal, again, the derivative of sine is cosine, so it'll be the cosine of x plus 2 times the derivative of what's inside the bracket, times the derivative of x plus 2. And the derivative of that is just 1. Derivative of x is 1, the derivative of a constant is 0, so it's 1 plus 0, which is 1, times the cosine of x plus 1, x plus 2, excuse me. So there's the derivative of the sine of x plus 2. Number 3, y equals the sine of kx plus d, so dy by dx. Again, the derivative of sine is cosine of kx plus d times the derivative of what's inside the bracket. And so you're differentiating with respect to x. Okay? You're differentiating with respect to x. Let me just move these over. Because it's dy by dx, that's the derivative of y with respect to x. So that means any variable that doesn't have an x is a constant, right? So when you take the derivative of what's inside the bracket, the x is to the power 1. You're going to multiply the 1 because it comes a coefficient in front, times the k, and then the power on x becomes 0 because it decreases by 1. So it's going to be 1 times k times 1, or just k. And when you take the derivative of d, that is a constant. And the derivative of a constant is always 0. So k plus 0 is just k. And so that's a constant. It comes in front. So there's the value of that derivative. Coefficient of k. Number 4. Again, the derivative of sine is cosine. So dy by dx is found by using the chain rule. The derivative of sine is cosine, so you take cosine of x cubed and then multiply by the derivative of what's inside the bracket. And the derivative of x cubed is 3x squared. So there's the value of that derivative, an expression. Number 5, sine cubed x means the sine of x all cubed. So again, when you differentiate this using the chain rule, the 3 comes in front, the power is decreased by 1 to 2, and then you take the derivative of what's inside the bracket, which in this case is the sine of x. And the derivative of sine, again, is cosine. So you're going to have 3 times the sine of x all squared, which we can write as sine squared x, times the derivative of sine x, which is cos x. So there's the value of that derivative. Number 6. Again, this is the same thing as y equals the sine of x squared minus 1 all to the power 3. Because that's what sine cubed means. So to differentiate, again, we use the chain rule. That means your first step is a 3 comes in front, and then the power decreases by 1. times the derivative of what's inside the bracket, which in this case is the sine of x squared minus 1. That's our first step. So I'll have 3 sine squared x squared minus 1. The derivative of sine x squared minus 1. So you're going to have to use the chain rule a second time now. To find the derivative of sine of x squared minus 1, we need to use the chain rule a second time. The derivative of sine is cos, so it's the cosine of x squared minus 1 times by the derivative of what's inside the bracket. The derivative of x squared minus 1 is 2x. So that 2x multiplied by the 3 in front becomes 6x. Sine squared x squared minus 1 times the cos of x squared minus 1. So there's the value of that derivative. Number 7. Have to use the product law for this because the original expression is a product. The first factor is x squared. The second factor is cosine x. So the derivative of the first factor, which is 2x, times the second factor, plus derivative of the second factor, and we saw that the derivative of cosine x was negative sine x, times the first factor of x squared. So we can write this as 2x cos x minus x squared sine x. And if you wanted to, you could take out a common factor of x out of there. It doesn't really help us in any way, but it wouldn't be wrong if you took out a common factor of x. It would only come out of the 2x and the x squared though, right? Not the sine x or cos x. Right? Number 8. Again, chain rule is used. The derivative of cosine is negative sine of negative 2x times the derivative of what's inside the bracket. And the derivative of negative 2x is negative 2. So the negative 2 will come in front. And there's your derivative. Sorry? Oh, because there was a negative there originally, yes. Now, one other thing about this, though, is when we see a rotation angle, a negative rotation angle, it means you're going clockwise, which would put this in the fourth quadrant, where sine is negative. So you could also write this as negative 2 sine of 2x, because negative 2x puts you in the fourth quadrant, and the CAST rule tells us that's our C quadrant. Only cosine is positive, so sine is negative. So either one of these is acceptable. If you were checking answers in the back of the book, though, they may do that last step, and that's the reason why that is true. Okay? So in this case here, we're going to have to use implicit differentiation because we have a term that doesn't involve x, it involves the letter y. So the derivative of sine x is cos x plus, And to differentiate, use implicit differentiation for that second term, you use the chain rule. So the derivative of sine, again, is cosine, so it'll be the cosine of y times the derivative of y with respect to x, which is dy by dx. And on the right side, the derivative of a constant is 0. So this is implicit differentiation because that second term doesn't involve the variable x, it involves the variable y. And to do that, we use the chain rule, which means you're multiplying by the derivative of what's inside the bracket. And what's inside the bracket is just the letter y. The derivative of that is dy by dx. And then like we did before, we need to get the dy by dx by itself by subtracting cosine x from both sides and then dividing both sides by cosine y. So there's our derivative. And again, we have used derivatives to find the slope of the tangent so that we can find the equation of the tangent line. So remember, that also involves knowing what both coordinates are at the point of tangency. So let's start there. Let's find out what y is when x is pi on 6. So I'll have the sine of pi on 6 over the cosine of 2 times pi on 6. Or the sine of pi on 6 divided by the cosine of pi on 3. Pi on 6, the coordinates are root 3 over 2, comma, a half. So the sine is a half. And that's divided by the cosine of pi on 3, which is also a half. Divide something by itself, you get 1. So the point of tangency will be the point pi on 6, comma, 1. And to find the slope of the tangent, we use the derivative, which in this case we'd have to use the quotient rule. Derivative of the top, derivative of sine x is cos x, times the bottom, which is cos 2x, minus the derivative of the bottom. The derivative of cos 2x will be negative sine 2x times the derivative of what's inside the bracket, which is just 2, times the top, which is sine x, all over the bottom squared. So we can simplify this a little bit. We'll have the cos of x times the cos of 2x. So those two arguments are not the same, so you can't combine them. Same thing with the second term. We can't combine the sine 2x and the sine x, but we can change the minus minus to a positive and bring the 2 in front. So it'll be plus 2 sine 2x sine x all over cos squared 2x. And really that's all we can do to simplify this. I mean, if you wanted to, you could do a replacement if you wanted to for cos 2x and sine 2x, but it's not really going to help us out much. It's not really going to simplify it in any meaningful way, so we'll just leave it as is. But now we can find the slope of the tangent by letting, again, x equal pi on 6, because that is the x value at the point of tangency. So it'll be the cosine of pi on 6 times the cosine of 2 times pi on 6 is pi on 3, plus twice the sine of pi on 3 times the sine of pi on 6, all divided by the cosine of pi on 3, all squared. At pi on 6, the coordinates are root 3 on 2, comma, a half. So the cosine is root 3 on 2. At pi on 3, the coordinates are 1/2, comma, root 3 on 2. So the cosine is 1/2. plus 2 times the sine of pi on 3 is root 3 over 2, and the sine of pi on 6 is a half. All over the cosine of pi on 3, which is 1/2, all squared. So this will give us root 3 over 4 plus 2 times root 3 over 4, or just root 3 over 2. But let's leave it as 2 root 3 over 4, because now we have a common denominator. And then that's divided by 1/4. So again, we can add these two terms together inside the bracket. 1 root 3 plus 2 more gives us 3 root 3s over 4 times the reciprocal, which is 4 over 1. The 4's cancel, and you're just left with 3 root 3. So there is the slope of the tangent line. This is our slope. And now using point slope, y minus y1 equals m bracket x minus x1, we can write our equation. Okay. The point of tangency again is the point pi on 6 comma 1. So y1 is 1. M, our slope, is 3 root 3 bracket x minus pi on 6. So you're going to get 3x root 3 minus, when you multiply 3 root 3 times pi over 6, you'll get 3 root 3 pi over 6. So y minus 1 will equal 3x root 3 minus pi times root 3 over 2. If we multiply all the terms by 2 to get rid of the denominator, we'll get 2y minus 2 equals 6x root 3 minus pi root 3. And if we write it in general form, we would bring all the terms from the left over to the right. We'll get 6x root 3 minus 2y negative pi root 3 plus 2 equals 0. So there's the equation of that tangent line at the point where x equals pi on 6. We've used derivatives in many ways to help us sketch graphs. So we'll apply the same stuff, same steps to sketch the graph of x minus cos x. So the first thing is we can look at that and we can see that there are no restrictions on x. It's not a rational function. It's not a radical. So the domain goes from negative infinity to positive infinity. There's no restrictions on x. So we often looked at that when we were sketching graphs. Secondly, we often found our intercepts. The x-intercept is where y equals 0. It's where x minus cos x equals 0. Now, in this case here, you can't solve this algebraically. It can't be done. So you wouldn't be able to find the x-intercept algebraically. It's actually at approximately 0.74, but there's no way you can do that algebraically. But once we find all the other pieces, we're going to have a pretty good idea of where this graph crosses the x-axis, just by using all the other points that we're going to find. But we can find the y-intercept by letting x equal 0. So it'll be 0 minus the cosine of 0. The cosine of 0 is 1 from the unit circle, and 0 minus 1 is negative 1. So our y-intercept is at the point 0, comma, negative 1. So there's that. So next we'll find our intervals of increase and decrease by finding the first derivative. If f at x equals x minus cos x, then f prime x, the derivative, will be 1 minus, now again, the derivative of cosine is negative sine x, so you're going to have a second negative sign there, and a minus minus becomes a plus positive. And we want to know where this equals 0. So that'll be where the sine of x equals negative 1, when you subtract the 1 from both sides. And the sine of x equals negative 1 only at 3 pi on 2. Now, it also tells us that we want to graph this between negative 2 pi and positive 2 pi. So there'll be a second point at negative pi on 2. Now, we could do this. We could put these 2 points on the unit circle, or on the number line, right, like we did before. However, let's look back at the expression. We want to know where 1 plus sine x is equal to 0. Because this tells us where our critical numbers are, right? And which is what we've done. However, remember the graph of sine x goes up to 1 and down to negative 1. This plus 1, if we put it on the end instead of at the start, means the graph is shifted up 1 unit, which means that this graph is never negative. It could be 0 at 3 pi on 2 and negative pi on 2, that is true, but it's never negative. So that means that the first derivative is never negative, it's always going to be positive. There are a couple places where it's 0, but every other place the graph is above the x-axis, meaning the value of it is positive, meaning that the graph of x minus cos x is always increasing. So let's erase this part because we actually don't even need it. That's how we would normally do it though, right? Find our critical numbers, divide the number line up. But we would see that on that number line in all those intervals, the derivative will always be positive because 1 plus sine x is never negative. So you can say that 1 plus sine x is greater than or equal to 0. So the derivative f prime x is always greater than or equal to 0. So f at x is always increasing. Okay? So the next thing we did is we found our second derivative. I guess let's back up a second. Because it's always increasing as we go left to right, that means f at negative 2 pi where it starts is going to be a minimum, and f at positive 2 pi where it ends is going to be a maximum. Okay, so we will deal with that when we start graphing. But again, we use the second derivative to find out concavity and any points of inflection. What are you laughing at?
All of a
Yeah. It is wiggling. Okay, so second derivative. If f prime x equals 1 plus sine x, then the second derivative, f double prime x, well, the derivative of a constant is 0, and the derivative of sine x is cos x. So f prime x just equals cos x. And again, we want to find where that equals 0. And the cosine, which is the x value, equals 0 at pi on 2, because the coordinates there are 0, 1. 3 pi on 2, because the coordinates there are 0, -1. But also remember that we're going also between negative 2 pi and 0. So it'll be negative pi on 2 and negative 3 pi on 2. So this is where we're checking for concavity and points of inflection. And we need to check all these intervals. So starting from negative 2 pi to negative 3 pi on 2 to negative pi on 2 to positive pi on 2, positive 3 pi on 2, and positive 2 pi. So we can use our calculator to help us here, or actually we can just use the cast rule. So this is 0, this is pi on 2, pi, 3 pi on 2. If we write in negative angles, this would be negative pi on 2, negative pi, negative 3 pi on 2, and negative 2 pi. So between negative 2 pi and negative 3 pi on 2, everything is positive there, including cosine. Between negative 3 pi on 2 and negative pi on 2, that's our S and T quadrants. Sine and tangent are positive, but cosine is negative in both of those. Right? Cosine is our second derivative, so that's what we're talking about, cosine. Between negative pi on 2 and positive pi on 2, you're either in the C or the A quadrant where cosine is positive. From pi on 2 to 3 pi on 2, you're either in the S or the T quadrant where cosine is negative. And then from 3 pi on 2 to 2 pi, again, cosine is positive. So that means it's going to be concave up, concave down, concave up, concave down, and concave up. And because the concavity is changing in all those critical numbers, those are all going to be points of inflection. So there will be points of inflection at f at negative 3 pi on 2, f at negative pi on 2, f at positive pi on 2, f at positive 3 pi on 2. So these are points on the original graph. And our original graph, the equation is x minus the cosine of x. So at negative 3 pi on 2, it'll be negative 3 pi on 2 minus the cosine of negative 3 pi on 2. And the cosine of negative 3 pi on 2 is 0. So this is going to be negative 3 pi on 2 take away 0, or negative 3 pi on 2. Our next inflection point is at negative pi on 2. And at negative pi on 2, again, the cosine is 0. So it's going to be negative pi on 2 minus 0, which is negative pi on 2. At positive pi on 2, again, the cosine is 0 at all these critical points. So in every case, it's just going to be the same as the x value. This kind of also tells us that probably the best way to sketch this graph is to have our scales on the x and the y axis in terms of pi, because we need to put these 4 points on there. This is where our points of inflection will be happening. So let's do that. So this is pi on 2, pi, 3 pi on 2, and 2 pi, negative pi on 2, negative pi, negative 3 pi on 2, negative 2 pi, that's pi on 2, pi, 3 pi on 2, and 2 pi. Negative pi on 2, negative pi, negative 3 pi on 2, negative 2 pi. So our first point of inflection is negative 3 pi on 2, negative 3 pi on 2, that's there. The next one is at negative pi on 2, comma, negative pi on 2. The next one is at pi on 2, comma, pi on 2. And then at 3 pi on 2, comma, 3 pi on 2. So that's that point right there. Our y-intercept is at negative 1. And the value of pi on 2 is 1.57. So negative pi on 2 will be negative 1.57. So the y-intercept would be approximately there. We're going to start at negative 2 pi. That's our minimum. And the cosine of negative 2 pi will be negative 2 pi. Take away the cosine of negative 2 pi. It'll be negative 2 pi minus 1, because the cosine of negative 2 pi is 1. So our minimum is at negative 2 pi, comma, negative 2 pi minus 1. So it's going to be down here somewhere. And then the maximum will be at 2 pi, comma, 2 pi minus 1. Approximately right there. In our first interval, we're concave up. And that starts from negative 2 pi to negative 3 pi on 2. We're concave up. Then there's a point of inflection, and we're concave down. Another point of inflection, and we're concave up, and we go through the y-intercept. And like I said, by following all these points, we're going to see approximately where the x-intercept is. Then we go to concave down, then to concave up to finish off. And there's a sketch of that graph. Right, so those are the questions that you should work on. Practice. L. A through L. I will post those to Google Classroom so you can check your work.
I'm pretty sure it's today. Like it's organic